So next up, we have Carl Hibbitts talking about a conundrum in the observed diurnal spectral variation of water on the moon, a spicy topic.
Thank you. Can you guys hear me? Hello?
Yes, I can hear you.
Okay, good. All right. Thanks for the introduction and thanks for the opportunity. I will be presenting a concept to resolve this conundrum in basically the kinetics and the flux of solar wind protons for the production of OH and its variation over a diurnal time scale. I want to acknowledge Survey as well as my co-authors for contributing to this. So basically, a bit of a background, space weathering is affecting the surface of the moon because it's airless. A combination of solar wind protons, galactic cosmic rays, UV, micrometeoroids are all pummeling the surface. And as you can see in the image on the lower left from Noble et al., it produces a rind, maybe 100 nanometers thick, that contains amorphous materials, nanophase iron. And it's within this rind that the solar wind protons are implanted. And you can see this schematically in the lower right-hand corner, where the protons can form essentially OH. And this is a process theorized more than 50 years ago for the production of OH on the surface of the illuminated moon. And I want to point out that we're now transitioning to talking about the illuminated moon, not the PSRs. And we're talking about abundances of, tens to hundreds of thousand ppms, not percentages. So this theory was re-enlivened, I suppose, back in 2009 upon the discovery of a 3-micron absorption feature in the spacecraft observations of Cassini epoxy, as well as M-cube on Chandrayaan 1, with the example of epoxy shown in the space weathering schematic on the upper right. And if sufficiently warm, which means at non-polar latitudes, it's possible that thermal migration will occur with these protons, and that the OH can effectively migrate to form potentially H2 that can resolve as gas bubbles or migrate out as H2, or potentially even desorb as OH or H2O. But there are conundrums with this. I'm going to start with some other considerations we need to keep in mind. Is that the solar wind has very limited penetration depth. Only grains that are directly exposed to the protons will have implanted solar winds in them. That'd be the very top grain, possibly a grain or two beneath that, due to potentially saturations in the upper grain, which does take on the order of years to 100 years, could deflect the incoming protons to impact subsurface grains as well, maybe the top grain or one beneath that. And the OH then will desiccate from those grain rims that are not exposed or replenished from the solar wind over the time that it takes to desorb. Okay. Now, this will result in two considerations. At the polar latitudes, shown on the lower left, it's very likely that the temperature is low enough that the migration will not occur, and that the grain rims will have OH on them, all of them will, and that due to micrometeoroid mixing, not really forming plumes, but mixing, that we'll have a well-mixed regolith of grains with OH on rinds throughout that. So we'll have a nice column of OH-rich grains on the rims. However, at non-polar latitudes, as we're just discussing, the OH will desorb from the rims and not being replenished by the solar wind. You only have a very superficial effect. Now we're getting into a potential conundrum and the solution to the conundrum. Conundrum being that the solar wind deposition and thermal desorption, the solar mechanisms are not consistent with observations or models. Solar wind implantation is simply too slow. But to explain the implied abundance variations that are large and rapid, it takes decades, as I mentioned, to saturate a grain surface with solar wind protons. And modeling suggests that only tens of ppms can be lost during a diurnal variation, which is an order of magnitude smaller than is suggested by the IR observations themselves. But I do want to say it would be consistent with the UV observation by Hendricks et al. The second conundrum is that OH loss is strongly temperature dependent, as I mentioned. Yet a diurnal variation is observed in telescopic observation at latitudes where the surface remains too cold for water to migrate. How can that be? It's going the wrong way. So let's go with observations relatively quickly. Here we're starting with Mare, Jessica Sunshine epoxy data. We see low, shallow absorption band, noon, equator. In the morning, equator, because we're looking down at the South Pole, North Pole. So this is the equator. We're looking at the equator along here. This is noon, this is morning or evening. The band deepens. Similarly for highland material, equatorial highlands, shallow band, deeper bands, in this case, evenings. So this is dependent on time of day, but another way to look at it, it's also dependent on incidence angle, where the band depth is directly or is proportional to the incidence angle. When the sunlight becomes more grazing, the absorption band gets deeper, both for highland materials and for marine material. And this is seen also in telescopic data as well. This is from Hannibal et al. 2020, showing that morning afternoon observations consistently show greater abundance. These are the chords, and this is some of the data that's been plotted. This is the equator, different latitudes. What I want to point out is that there is even a diurnal change. This is hours from local noon, so this is about noon. This is either morning or evening. That there's diurnal variation at poles, which is inconsistent with the physical motion of OH. Okay, and this trend is conserved when viewed in terms of incident angle. I took 0 degrees latitude here, the equator, because that's where we calculate incident angle for the sun without worry about alternator observations. So you can see that it generally has this kind of slope to it, consistent with early observations. Caveat, emission angles will not be negligible and can affect some of these interpretations, especially for telescopic observations. But talking about global distributions, we go to M cube data. This is the typical one that we see. Overplotting the data from the work for Hannibal et al., actually symmetrizing it, inverting it back and forth, it correlates more or less. The point is that both the latitudinal distribution and diurnal effects are consistent with effects due to or correlate with incidence angle. So how can we explain this? I'll propose that these observed variations are primarily due to the effect of incident angles coupled with the unique but largely stable distribution of OH in the grains rims. That if the OH is stable over longer than illumination, but not totally stable, then some will be lost, as has been modeled by Grant Jones et al. 2018. In the polar regions, none will be lost. And even though you have dominated by surface scattering, most of the light penetrating shallow and interacting with rims of grains along the surface and coming out. The changes some with the time of day, but always rather grazing will always have a deep IR band, getting deeper at more grazing angles, but always deep. Compared to non-polar morning or evening, still grazing, still have a relative deep, but not as deep IR band at the poles because one is sampling preferentially the OH-rich rims on grains at the surface. Compared to non-polar observations during midday times when the light is more vertical, the reflected illumination is from grains that have less OH in the rims due to volume scattering. And this is also consistent with UV observations. That even though UV observation or the UV absorption band, by the way, is 7 orders of magnitude stronger than the 3 micron feature, a very strong diurnal band is not seen, which is seemingly inconsistent unless one considers the fact that UV only penetrates the very first grain. It does not penetrate into the desiccated layer.
Carl.
Thank you very much.
2-minute warning. Thank
you. And thus, any diurnal variation on UV is going to be a real diurnal variation, a real loss of OH from the grain surface. The amount that is modeled by Hendricks et al. Is consistent with about 10 ppm bulk abundance variation, which has been modeled by Jones et al. So the UV observations are consistent with the models actually. And if you look at the diagram in slightly more detail, you can see the noon, midnight period, where at the equator, the absorption band can be deep, or the change is deep, whereas at the polar regions, the diurnal variation is almost nil, consistent with lack of mobility at cold temperatures. Caveats, it's not clear if the UV band is really indicative of OH, but most likely is because H2O is not going to be stable on the equator at all for detection. So these are the conclusions. We have 1 minute remaining. I'll just go over the recommendations that to resolve this or to truly determine if this is the case, we can do this potentially through remote sensing, through bidirectional reflectance distribution measurements of the lunar surface in the 3 micron region, through orbital missions such as IceCube and trailblazers that can look off nadir. Also, landed measurements, taking care to avoid landing plume effects that can scour the surface, are another way to potentially check the hydration of the surface and even the near surface. And of course, you need optical constants for appropriate materials. So I'll leave this up. and I'll end the talk now. Thank you.
Thank you, Carl. I think that's so timely and fascinating, and I'm excited to see where this goes.